The next speaker is Francesca Mignacco from Princeton University and the City University of New York Graduate Center, and she will be talking about optimal learning protocols via statistical physics and control theory. And I will warn you 5 minutes before the discussion should start. Okay?
Okay.
Take it from here.
Hopefully. Thank you. Let me just set the slides. Can you see my slides?
Yes.
All right, good. Okay, so thank you very much to organizers for having me online. I'm very sorry I couldn't be in person due to my visa requirements, but I'm happy to present this work about optimal learning protocols through a combination of physics and control theory. So optimal protocols are ubiquitous in the machine learning pipeline and affect all the components from the data to the algorithm to the architecture. So for instance, it's very common to introduce some strategies to select the data dynamically and picking, for instance, a good ordering for training. The algorithm involves a series of schedules for various hyperparameters, the learning rate, batch size, and so on. And also the architecture can be made dynamic by tuning some components of the model, for instance, some gating modules or pruning and so on. So all these variety of strategies share the goals of, on one side, speeding up the convergence, and on the other side, most importantly, improving performance by steering the dynamics towards some solutions with better properties. And however, all these strategies heavily rely on trial and error heuristics. So it is quite natural to ask whether there is something more principled we can say about their optimality. Where here I will always speak about optimality in terms of the final performance. So this is quite a natural question to ask, and if you want, it's a way of framing this problem as an optimal control problem, where in this case, the system, the dynamical system that we want to control is really the neural network itself. So the dynamics, the high dimensional dynamics of training the weights. However, precisely because of this, solving this problem directly in this weight space is computationally demanding. So the idea that we considered is instead use some tools from statistical physics that allow us in some specific cases to start from this training dynamics and obtain some effective low-dimensional descriptions of the learning in terms of a few order parameters that capture all the relevant information about the performance. And so once we have this description, we can apply control theory. Because it's a low-dimensional problem, we can apply standard control theory methods, and we also gain in interpretability because the order parameters are highly interpretable in general and tells you something about the dynamics. And so this is basically the main idea that I will consider here, and this framework will allow us to basically obtain a lot of schedules that here I broadly denote by U as like a control parameter, but it can actually be seen in a lot of different learning scenarios, and we illustrate this in our recent preprint. So just to fix the idea, I will consider a relatively general setup. That's what we do in this paper. We consider a data model that's a variant of this sequence multi-index model that was nicely explained by Ugo Cui in this review paper that allows as specific examples a variety of learning scenarios that we can then consider separately. So the data is simply drawn by a mixture of Gaussians with the generic means and variances, and the labels are generated through a teacher network with some hidden teacher weights here denoted by W star and possibly label noise. And the architecture will be some variant of a two-layer neural network, while the algorithm will be one pass stochastic gradient descent. So in practice, we define a cost function on each given sample that can involve a regularization term, for instance, on the L2 norm of the weights. And then we train each time step by updating the weights, taking a gradient step computed only on one example that we never see and use again. So it's why it's called online or one pass. And then, and this is really building on long-standing work starting from the 90s with the works of Sadensola and Biel and Schwartz, and then many more recent works. What's nice about this description is that it's actually possible to capture the high-dimensional dynamics in terms of a set of ODEs on some order parameters that describe the network, that are some scalar products or overlap between all the relevant directions in the problem, so the weights of the teacher and the student, and the centroids of the Gaussians that define the data. So basically, in the high-dimensional limit, where the number of dimensions of the problem and also the number of available samples are very large at a fixed ratio, we can obtain an effective, an exact low-dimensional description of the dynamics of the order parameters. And this is what we will use at our dynamics to apply optimal control. So in what's left, I will illustrate some examples in various learning settings. First, I will consider dropout. That's a regularization technique that we have studied in these two works with Francesco Mori. I will also consider denoising autoencoders, a different type of architecture, and also time permitting a different learning paradigm, continual learning, and how to tune automatically some continual learning protocols and the learning rate. And this is a work in collaboration with Francesca and Stefano Sarao Mannelli that appeared in iClear this year. So before starting, just there's various ways of solving this optimal control problem. One is through Pontryagin maximum principle. So basically, one way of solving this problem, starting from the dynamics of the order parameters, is a variation approach. So we define a cost functional that is basically depending on the perform or the error of the network at the end of training. And then we introduce some Lagrange multipliers or co-state variables, Q hat, where Q denote the order parameters that basically enforce the dynamics. And then by basically solving this variationally, we can find a set of forward and backward equation for the learning dynamics and for the constraints for the co-state variables that we basically need to iterate, and finally also condition for the optimal control for this schedule U that according to the different problem will represent a different training strategy or the joint optimization of various hyperparameters. And so this is the framework. And then I will provide the first example that's a bit more precise, and I will talk about the dropout regularization. This is a technique that was introduced more than 10 years ago now. And the idea is that at each time of training, each node of the network can be turned off with some probability or active with some other probability in such a way that not all the nodes are trained simultaneously, and this is done to reduce negative co-adaptations in their terms, or basically induces learning more robust representations. So in what follows, I will always call P the probability of a node of being active. So in practice, during training, there's this training phase where each node can be active with probability P. And then once the network is trained at test, all the nodes are used, but they are all rescaled by another factor, PF, to account the fact that they were not all trained at the same time. And so quite naturally we ask what is the optimal dropout probability? So what is the optimal way of choosing this value P? And we consider a simplified model of dropout to study this problem. It's a teacher-student problem where the data is simply Gaussian, the X are just Gaussian, and the labels are generated by a teacher, so it's a special case of what I explained before. The teacher is just a two-layer network, and there's some label noise, sigma. And the student instead, the student is also a two-layer network, but with dropout. So each hidden node of the student is paired with some activation variable. That's just a Bernoulli with probability P, and that defines basically if each node at each time is used or not. And then the full student network is used at the end. So first of all, we can ask what's the optimal probability of node activation if we keep it constant throughout the training. And it turns out that in this model, there's a lot of analytic results that can be obtained exactly. So in practice, we can, for instance, study different stages of the dynamics. And in the early time dynamics, we can compute the optimal activation probability as a function of all the other parameters of the model. So basically the degree of over-parameterization, so how many teacher and student hidden nodes are there, and the label noise. And so we can see that quite intuitively the optimal activation probability depends on all these parameters, and in particular it decreases when the label noise increases. So the noisier the labels, the higher the dropout. So we need a much higher regularization. And this is reasonable. And then what we can do is that we can also compute a phase diagram, looking at when it is actually optimal to drop out at all, versus when it's optimal to train with the full network. And we can see that this also depends on the parameters, the learning rate, the noise, and so on. So for instance, if we increase the size of the network, so if we increase the K hidden nodes of the student, the region in which dropout is optimal is bigger, because more regularization is needed because we are more over-parameterized. And so this is a series of results that you can obtain. And also through this model, you can more precisely account for the effect of dropout in terms of the order parameters. So basically, to fix the ideas, we can take just a teacher that has one hidden unit and a student that has two hidden units. And so we can basically say that the student, each hidden unit wants to align with W star, with the teacher. But during training, each of the unit would also develop an orthogonal component that is due to the noise. So what happens is that we can basically, through the order parameters, measure how correlated are these two components, these two noise components of the student. So this is what's plotted in the center of this panel as a function of time that we call negative coadaptation. So basically the red is no dropout and the blue is a dropout. And you see that these components that are not aligned with the teacher of the two different hidden nodes become more uncorrelated if we use the dropout more and more throughout training. And also on the left, we have the generalization error as a function of the training time. And you see that the blue line with dropout, in this case, it's picked optimally, can achieve a very large gap in performance, despite the fact that the cosine similarity, so the alignment with the signal on the right, is actually higher if we don't drop out. So basically, this is a case where a dropout achieves the best trade-off between learning the signal and don't overfitting the noise. Then we can turn to the more like dynamical question on what is the optimal dropout schedule. So in the literature, there have been also some proposals of dynamic dropout probability. In the original works, this activation probability was always kept constant between 0.5 and 0.8. Then some variants have been proposed experimentally, for instance, some form of annealings. And we were very curious to see if we could compute the optimal one in our simple problem. So in practice, we applied the machinery that we have we have defined before, and we find that the optimal activation probability as a function of time is decreasing. There's an initial plateau. So which means that at the beginning dropout is not used, all the nodes are active, and then the regularization is introduced more and more during training. And what we can do is that we can also check how it impacts the three quantities that I've shown before. So in terms of generalization, on the left, we see that the optimal one in black achieves a small gap compared to the optimal constant one. So actually an annealing and like a dynamic dropout, it's improving a little bit the performance. So if you instead look at the central one, what happens is that so at the beginning there is no dropout. So basically the co-adaptation is higher between the nodes for the optimal schedule, and then it starts decreasing. While the cosine similarity, this comes at an advantage for the cosine similarity because so basically the network is exploiting the fast increase of the cosine similarity, the alignment with the signal at the beginning of the training. And overall, this gives the best performance. And then we can see how the optimal schedule for dropout adapts to different levels of noise, for instance, so different parameters. And so in this case, we find that as we increase the noise in the labels, the initial plateau where no dropout is applied reduces more and more, which is also reasonable because noisier data require increased regularization. And so this basically is automatically obtained in the optimal schedule. Which also resembles some schedules that have been proposed in the literature. For instance, this curriculum dropout, that it does precisely this. So it has an initial, it's basically an annealing in the activation probability. So for this first part, basically we have, this is one application that involves the architecture. And then I want to consider another example, that's denoising autoencoders. This is a completely different architecture. More generally, denoising autoencoders are networks that are trained to denoise corrupted input. So this is a sketch from the paper that introduced this some year ago at ACML. So there's like the clean input is corrupted, is passed through an encoder, and then the network is trained to reconstruct it from the original one. And this architecture has also been studied theoretically recently. Both the dynamics of learning and the asymptotic generalization properties have been studied for denoising autoencoders. Also because of the recent interest due to their connection to diffusion models that can be parameterized by DIEs. And so here we will again consider a prototypical model that was also studied by Kui and Seborova in 2023, where again the input the clean input is given by a mixture of Gaussians, and then it's corrupted by some noise, some Gaussian noise Xi, with the given noise level delta. And the network is a two-layer network plus a skip connection. So we have this bottleneck network, if you want, with a few hidden nodes that produce a reduced representation of the data, and then instead just a scaling of the corrupted input. And so what we can do is that we can study the training of this denoising task via online stochastic gradient descent, and we can ask about optimal schedules. So first of all, in the noise level. So typically, what one could do is that one can train by using the same noise level to corrupt all the inputs during training. But instead here we ask, what if we use different levels of noise? And what if we tune optimally this noise schedule? And then we compute the performance with a fixed level of noise at the end of the training. So we fix a noise level delta F, we use it for our test data, and then we ask what's the best training schedule for the training noise. And here you can see, so on the upper left, different schedules for different values of the final noise. And also on the upper right, the percentage improvement of the mean square error compared to the schedule that used the constant noise. And so here what we find that we can also see from by looking at specific cosine similarities between the hidden nodes and also the skip connection, is that the optimal schedule, it's basically enhancing on one side both the restriction capability, the construction capability of the bottleneck network. So in a sense, the hidden nodes of the autoencoder are better at reproducing the clusters in the data. But also the skip connection, the training of the skip connection is accelerated in an optimal way, and this results in a percentage improvement of about 30%. Then another question that we asked is how to tune batches. So one can think of, instead of just having one noisy version of the input, to consider different, like an augmented batch. So basically taking different realization of noise and corrupt the same input with different versions of the noise, so that we have a batch and for training. And then we do basically mini batch online stochastic gradient descent with some given batch size. And then we ask, what if we can tune the size of the batch dynamically by constraining the total budget? So we say, okay, we have given number of examples and we want to distribute them optimally along training. And what we find is that basically the optimal schedule is some form of noise annealing, if you want, because you start with a smaller number of batches, so a small number of samples per batch, which means noisier gradients, and then you increase the number of samples towards the end, so to reduce the noise while training, and this is about a 10% improvement in the mean square error. And finally, what we can do is that we can, be a bit hopeful and say, we have a very simple, relatively simple model of the data because it's a Gaussian mixture, but what if we just fit the means and variances of this Gaussian mixture from real data, and then we compute the optimal schedules, and then we apply them to the real data training. So if you want, using this model as a small laboratory to find the optimal schedules that we can then apply to real data. This is just a simple example on MNIST. So as you can see here, I'm again considering the noise schedule And so even by eye, you can see below there's like different pictures of 0 and 1s, where the original, corrupted, constant, and optimal versions are displayed, and the optimal one is more distinguishable, and you can achieve in practice an improvement of the mean square error up to 30-40%. And so finally, I want to showcase just one last learning paradigm, that's continual learning. So this all these settings are just special cases of the model, the sequence multi-index model at the beginning. So this is very flexible because with the same basically the same technique, you can study very different problems. And finally, so continual learning is it's basically a setting where you want to learn multiple tasks. So imagine that you have 2 tasks. First, you train only on one task, and then you train only on the second task. And what typically happens is then, by then, you have forgotten the first task. That's called catastrophic forgetting. You have basically overwritten the weights of your neural network. And this is actually a problem that is encountered in machine learning experiments. So on one side, it's observed that both humans and animals can do this continual or like lifelong sequential learning without these forgetting problems, like relatively well, while in practice machines are prone to catastrophic forgetting, and this has been studied theoretically in several works recently. And we were interested in precisely this question. So if one technique to mitigate forgetting is called replay, which basically amounts to replaying or like presenting again some examples from the old task while the new task is learned. So if you want some version of revising, but then the order of replay is unclear, so one can think of interleaved replay, but we want to ask what is the optimal replay protocol. And again, we consider a simple model of continual learning, and where these 2 tasks are again an instance of the teacher-student problem from the beginning, where the teacher is just a single layer network, and instead the student is a 2-layer network with 2 hidden units. So the student has exact the capacity to learn both tasks if each node is tuned to one of the 2 tasks. But that's, I mean, not what would happen in practice. If I train sequentially, the student will first align both units to the first teacher, and then basically shift the other units to the second task, resulting in forgetting. So we want to do replay precisely to avoid this problem. So what we do is that now our control will be the identity of each sample, if you want. So first we memorize the first task. So there is, because we really want to study forgetting, so we start from a condition where for a long time we have trained on the first task so that we have learned it well and we don't want to forget. And the control is coming in the second phase of training, where we want to learn the other task without forgetting the previous one. So in this case, the control is just which one. And I haven't mentioned this, but we can also have a discrete, the control does not have to be continuous. We can have different type of controls. So if we don't do replay, this is what happens. So we have this first long phase where we only train on task 1, this second phase where we train on the task 2, and the performance is swapping. And it results on basically forgetting of the first task with the very bad performance on the orange one that determines task 1. If we do interleaved replay, so in the second phase we alternate between task 1 and the task 2, What we find is that overall the performance, here the average is this dotted line, is a bit better. However, if we compute the optimal, that's even better, and it reveals an interesting structure. So we find that, and this is quite robust, even if we change different problem parameters that I haven't even mentioned, but we consistently find this structure in the second phase, the phase of replay, that is basically first what we call one focus phase, where only the new task is presented, and then like a revised phase where the replay is introduced and the previous task is also presented in a shuffled way. And in this revision phase, the order doesn't really matter. So what we find is really this distinction between a focusing phase on the new task and then an interleaved phase. And so what we can do here is that we consider joint optimization of both the task ordering and the learning rate. And interestingly, so we have in principle one learning rate, but in practice what happens in the optimization we see is that we effectively have two curves. So basically when you joint optimize the task and the learning rate, you have that according to the task a different curve of learning rate must be used. So in this first, so in left I'm plotting the learning rate as a function of time only on phase 2, and the green part denotes the focus phase where only the new task is presented, and you see there's like an annealing of the learning rate, and then there are these two curves alternating in the revision phase between task 1 and task 2. And another important parameter that is the task similarity. So the task similarity has been studied. So how similar are these tasks? So in this case, how aligned are the teacher and the teacher of task 1 and the teacher of task 2? And again, you can see that interestingly, the optimal, basically the performance is non-monotonic with respect to the task similarity between the two teachers. And finally, we wanted to also test this strategy on real data. We call this a pseudo-optimal strategy, first because it's not obtained directly on real data, it's just an intuition. But also we don't need to precisely fit the data, because if this intuition applies, what we need to measure is, so basically what we noticed here is that the switch between the focus and the revision happens when the losses of the two tasks are matched. So basically the pseudo-optimal strategy is to train on a new task until you have learned it as well as the old task, and then start replaying in an interleaved fashion. And we have tried this on some real data sets, for instance here fashion MNIST, and we see that basically the pseudo-optimal strategy is consistently the best between no replay and heuristic like the interleaved replay. And it basically strikes really the balance between the two according to how many data points we have available. And the similar interplay is seen also on Cypher 10, where so basically we can also see that the pseudo-optimal strategy is the best between the two. And so to conclude, so what we found is that we can look for efficient learning protocols as an optimal control problem, but on a reduced description of the network, based on the fact that we can track the dynamics of the order parameters in some learning settings. And what we can find is that the strategies that we obtain are non-trivial, but to some extent interpretable in terms of the order parameters. And in some cases also we can apply them to real data. And this interpretation is often based on the presence of some learning trade-offs that have to be balanced by the optimal strategy. And we can also jointly optimize different hyperparameter schedules simultaneously. So we can also look at the joint role of different schedules. There's many open directions. First of all, considering more realistic data models with additional structure by incorporating some of the models that have been presented in the literature. Also here I focus on the online case. I think it would be very, very interesting to extend this to batch learning, to study memorization. And I have also focused on the performance, on the error, basically as the objective of the control problem. But in principle, other metrics could be used. For instance, some metrics that are used in like in fairness related to the balancedness of the data set, or other metrics that are more related to maybe the representation itself more than the performance. And with this, I conclude, and I thank you for your attention.
Okay, thank you very much. Paper is now open for discussion. Is this working? Yeah. Questions? Sorry? Yeah, somebody has to. There's a mic there, but does it switch on? First, we need questions. Yes, Patrick.
Hi, thank you very much. In the last example where you had you alternating between different tasks, does it matter what the order in which you present the tasks? Does it learn one of them better, the first one better than the second one, or is the final end point the same?
All right, this is a very pertinent question. In this precise problem, the task do not have a notion of relative difficulty. So the tasks are all equally difficult. So in this case, which of the two is, if I swapped task 1 and task 2, the picture would have been the same. But this is not the case in general, because tasks in general are not equally hard. And there is another setting that I have not presented, but we have studied, that's called curriculum learning, where in practice the dataset has different levels of complexity or difficulty among the tasks, and it turns out to be useful to order the difficulty. And these have been studied. So curriculum is usually easy to add. So for instance, in some cases, presenting all the easy tasks before and then the hard, increasing the difficulty is the best thing, but not in general. And it's something we study in the paper, but I did not have time to present. So thank you for asking that.
Yes. Oh, sorry. Was the yeah.
He actually put his hand up.
Oh, sorry. You already had. I didn't realize. Sorry.
Thanks for the very interesting talk. One question I had was you converted the gradient descent problem to the set of differential equations, and you mentioned low dimensional representations. I guess I missed, how are you taking this set of ODEs, which is originally very high dimensional, and how are you identifying the right order parameters, the right low dimensional variables to work with?
Okay, yeah, that's very important. So in this case, so very, I think that the quickest way to see this is that you are online, you see new examples at each time, the data is Gaussian, and all that matter is the network pre-activation. So if you want the scalar product between the data and the weights of the network and so on. And these are low dimensional Gaussians. And so all that matters is basically the means and covariances of these Gaussians, and these are the order parameters in this problem. And given that the network is small, so the width stays of order 1. You have a finite number of pre-activations that keeps the order parameters finite. But you are right that in general, finding a good order parameter is the most important thing.
Okay. Okay, so there's time for a very short question. If you think you could also give a very short answer.
So in the example that you gave about the catastrophic forgetting, in your case, it seemed like it was related essentially to redundancy within the network, right? You have two nodes that essentially learn kind of the same weights. Is there a method of regularizing to avoid redundancy within each layer? So, making sure that, say, that vector of weights, has a dot product that's nearly zero or something like that, or is that computationally infeasible?
I'm not sure I understand the question. The first thing that comes to mind is the dropout, in the sense that what I showed before is that you reduce the redundancy between the two learned representation if you do dropout. Of course, if you are training always the same task, then it doesn't matter because they're both learning the same task, but maybe they interleave the phase. This can help.
Okay, thank you very much.